All right, so working through the 3-question review for the trigonometry unit. Ideally, you've tried all these already. Start by solving an equation in which I only want to look at values between -2 pi and 0. Slightly unusual restriction. First, I look at my factors here, and I need to think about where does the cosine of x equal -1/2, and separately think where does the sine of x equal +2/3. All right, cosine where equals -1/2. I can figure that out exactly without a calculator. And first, let's think about where cosine is negative. Cosine is negative in the third and the second quadrants. And they must have a reference angle of 60 degrees or pi/3 because the cosine of pi/3 is 1/2. So I'm looking for angles that end up right here. And well, if I look at this angle from here to here, keep in mind that is not within my restriction. I only want to look from angles from -2 pi to 0. So my first negative answer will actually be from here to here. And that angle there is -2 pi/3. And there's also this angle from here to here, which is -4 pi/3. So those are two of my answers. Then looking at the sine function, I will need a calculator because we're not expected to have memorized where sine equals 2/3, but it must be possible in two places, and sine is positive in the first and the second quadrants. The reference angle, however, will require using a calculator. Make sure it's in radian mode, and if you go the inverse sine of 2/3, we should get approximately 0.73, which means the reference angle in radians is approximately 0.73. And again, I want my two first negative angles. And so looking right here, this angle from here to here is my first negative solution for this part. And that would be -pi as take away another 0.73. So that's approximately -3.871. That's just me going -pi minus 0.73. And I also have this angle from here to here, which there's various ways of calculating. It's almost -2 pi. It's -5.553. And so in this case, I had two exact solutions, two approximate solutions in this restriction. For the second equation, I have no restrictions. X can be any real number, but I have a messier equation. The key to this is realizing this has elements of the double angle identity for tangent. And if I divide both sides by 1 minus tan squared x, I realize that I'm highlighting is the double angled identity for tangent. And so instead of writing 2 tan x over 1 minus tan squared x, I'm going to write it as just the tangent of 2x. On the other side, I have 1 minus tan squared x divided by itself, so that equals 1. All right, so how do I solve this? Well, first let's think about where tangent equals 1, which, if I just ignore the 2 for a moment, where tangent equals 1, that's at 45 degrees, or pi/4, and 5 pi/4. And so those values of pi/4 and 5 pi/4, which keep going, in fact, the next one would be at 9 pi/4. Those are not my solutions for x, those are my solutions for 2x. That said, I want to divide all of this by 2, which means I want to divide all of this by 2. Or in practice, I want to multiply each of these by 1/2, which is quite quick. And I can now see my list. X is exactly, and the list actually doesn't have a beginning or an end. So I have pi/8 being my first positive solution, followed by 5 pi/8, and 9 pi/8, and on and on and on. So I want to summarize this list, and in the end, I can summarize it quite quickly by saying x equals just pi/8 plus the distance from each one of these is just the period, and that is exactly pi/2 every time. So I can summarize this by saying the general solution is pi/8 plus any multiple of pi/2, where n belongs to the integers. All right, so here I have a wave composed of two other waves. I have one in green, one in dashed. And I want to find the equations of each of these. So let me look at the graph in green here. So first of all, if I want to find the equations for any of these, I need to figure out the amplitude, and which is halfway from from 4.4 to negative 8.4. And so that amplitude is 6.4. And the center line is halfway between 4.4 and negative 8.4. And the center line is negative 2. And then the amplitude is a distance from the center line to the top or the bottom. Either way, I get an amplitude of 6.4 and a center line of negative 2. I need to find the period, which if I look from here to here, that is half my cycle, which means from 0 to 5, that's half my period, which means the period is 10, which means my B parameter is going to be the same as 2 pi divided by 10, or just pi over 10. And what's left now is to determine what kind of function I want to use. Well, if I just imagine this continuing, my function is starting at its maximum. When x is 0, I have a maximum, which is how cosine behaves. So I definitely want to use a cosine function. And I can say y equals 6.4 times the cosine of pi over 10. Because it's starting at a maximum, as does the cosine function, I don't need a phase shift. Plus my k value, or take away 2. Now, while this is great, technically, this is a little bit wrong, because this that I have here, this is a wave that goes on forever, when really it only begins at 0 and ends at 5 on the x. So a little bit better is to put a little restriction on the x here and say where x is between 0 and 5. All right, similarly, looking at the other wave from here to here, same ideas. And so I want to find my amplitude and center line first. The center line being halfway between negative 8.4 and 0. So my center line for this must be negative 4.2. The amplitude being the distance from the center line to the top or the bottom. The amplitude must be 4.2. And the B value being 2 pi divided by the period. The period, I can see, goes from 5 to 15, but that's only half the wave again. This distance from here to here is not the entire wave. So 5 to 15 is a distance of 10, times that by 2. The period is 20, or B is pi over 10. Now I'm ready to come up with my equation. That said, I want to use a cosine function again, because cosine functions are easiest to determine if we are given either maximums or minimums, and that's what I've been given. However, neither of these is right on the y-axis, so I do need a phase shift. So because I need a phase shift regardless, I'm going to focus on this maximum over here. And so say the cosine function, I'll use a positive cosine function. So I have positive 4.2 times the cosine of pi over 10 times x. This time, if there is no phase shift, that max would be right here. This is what it would look like. That's a terrible drawing, but that's what this would look like. That maximum would be right on the y-axis if there was no phase shift, and it's not there. So I have to imagine that maximum being translated 15 units to the right. So I want to subtract 15 from this. And then my center line. Now, again, I really should have a restriction on here, because this wave begins at 5 in the x and ends at 15. And so I should say 5 is less than or equal to x, which is less than or equal to 15. That's it. Lastly, it would be pretty much the same idea to use a negative cosine function. You'd have an extra negative, so I wouldn't generally recommend it. But it would, if you had negative 4.2 times the cosine, everything would be the same. Except now we're looking at a minimum, and we're imagining this minimum translating from here to here. So 5 units, so I'd have a minus 5 with the same restriction we have there. But because these are both such similar equations, I'd generally deal with an equation that has less negatives than I have to use. Lastly, I want to sketch a graph of a pretty complex looking function. So how can I do this? Well, if I look at this here, first of all, let's look at the sine of 4x. I can think of that. I can use my double angle identity for sine. Because if I think of that as the sine of 2 times 2x, which is definitely the same thing, I can imagine me looking at where I have, well, maybe I'll say this. Instead of, if I just look at this, the sine of 2x, if we know that that equals this, well, then imagine instead of an x, I have a 2x, which means these x's here would be 2x, which means I can write my denominator as 2 times the sine of 2x times the cosine of 2x. And I can do something similar with my numerator. I can use my double angle identity for cosine. First, by imagining cosine, instead of cosine 4x, I'm going to write it as the cosine of 2 times 2x. And again, I have a choice of a few different identities for cosine. But if I look at my numerator, I'd like that 1 to cancel out. And so in that case, it'd be more helpful if I think about this identity. Sorry for cosine. I've been talking too much lately. Cosine of 2x. If I just think about this, where it's 1 minus 2 sine squared x. Well, again, imagine that x right there being a 2x, which means that x right there would be a 2x, which means I can write this as 1 minus, bracket, 1 minus 2 sine squared 2x. All right, so now let me see what I have. In my numerator, if I get rid of those brackets, I have 1 minus 1, which is 0. I'm subtracting a negative, so I have a positive. So I just have 2 sine squared 2x over 2 sine 2x cos 2x. I can cancel these out, so that's good. As well, if you look at my numerator, sine squared 2x means the sine of 2x times itself. I have a factor of sine 2x down here. So I can also cancel one of these sine 2x's out. And so all I have left is the sine of 2x in my numerator and the cosine of 2x in my denominator, which is equivalent to a tangent function, the tangent of 2x, which means this function I gave you, f of x, is the same as the tangent function with a single transformation, being a horizontal compression by a scale factor of 1/2. So let's imagine my tangent function here. The tangent function starts at 0. In fact, actually, before I go on, I'm going to draw the asymptotes. The graph of tan x has an asymptote at pi over 2 and 3 pi over 2. However, there's a horizontal compression by a scale factor of 1/2 right there. That means my asymptotes are not, for example, this first asymptote is not at pi over 2, it's at pi over 4. So it's right here. And this next asymptote, instead of being at 3 pi over 2, is at 3 pi over 4, which is right here. And tangent is periodic, which means once we see the period, we can just repeat it, which means I can just see there must be another asymptote here and here. And my voice is going. And so at this point, I can hopefully see the wave that this must go up like this. And then there must be an x-intercept at each of these points. And so I'll just quickly draw these as my voice grows more and more hoarse. Oh, that's an alarm going off. I guess it's time to wake up. All right, so with that said, keep in mind, what I just graphed is quite quick if I remember what the graph of tan x looks like, and then just compress it horizontally by a scale factor of 1/2.